Hello, my name is Fernando Treviño Ramirez, and today I'll be explaining the lower bound proof for the element distinctness problem. This is for my algorithms class. Let's begin by defining the problem. The element distinctness problem asks if all n elements in a given array are distinct. We're expecting a yes or no answer. For example, on this array, we have the element 5 repeating, therefore we will say no. The array is not distinct, and for this example, none of the items are repeating, therefore we will say yes, this array is distinct. For the model of computation, we will use the comparison, so we can do less than, equals, or greater than, and we can do operations like is x greater than y, and we will only receive one of two answers: yes, x is greater than y, or no, x is not greater than y. So the task that we have is that we need to prove that this problem cannot be solved in a small O of n log n comparisons. The best we can do is big omega of n log n comparisons. Note that this doesn't mean that the best or average case will need this many comparisons. Only the worst case is necessary to satisfy this time complexity. When trying to do a lower bound proof, it is often a good idea to try and describe how the decision tree will look like. For example, let's say that we have a given input array of n numbers, going from x1, x2, all the way to xn. We can think of the decision tree as a binary tree where at each node we can ask a question. For example, at the top of, we can say, is x1 equal to x2? If the answer is yes, then we're done. We can report that the answer to the big question is no. The array is not distinct because x1 is equal to x2. But if the answer was yes, then we will do some more questions until we can finally get to a solution and either report a yes or a no to the big question. Note that we report an answer once we reach the end of a branch, or in other words, if we reach a leaf. So the question is, how many leaves do we need? Well, to answer a no, that means we have done an equals comparison that resulted in a true statement. And to reach that conclusion, it means that we have reached a leaf node for each of the possible pairs. For example, x1 could be equal to x2, or x1 could be equals to 3, so on until xn. Then we can say the same thing for x2. But since we already covered the case for x1 being equal to x2, we can argue that we can omit that question. So if we count all possible solutions, we end up with n distinct solutions for column 1, n minus 1 solutions for column 2, all the way to n with just one solution, which is the yes solution. The problem with this approach is that the sum of all these solutions is less than n squared. And if we think of a decision tree, the number of questions or comparisons that we need to do for the worst case, it will be the height of the tree itself. So the smallest tree that we can make with n squared leaf will be log of n squared, which is less than n log n. So is that it? Did we just prove that we can do better than n log n? Well, no, sadly. This is an incomplete analysis. We need to expand the yes solutions because there might be some information missing on those. To count all the yes solutions, let's consider the smallest case where we have an array of 2 items. If we consider those arrays to be input pairs, we can plot them in a graph and we will notice that all the pairs that will guide us to a no answer will be of the type 0, 0, 1, 1, 2, 2, and after plotting them you will get this nice line with a slope of 1. And if we look closely, all the pairs x, y above the line share the same property, that x is less than y. So if we ask, is x less than y, or x greater than y, or x equal to y, we will always get the same question for any point above the line. Same thing we can say for the other side of the line. If we ask the same question, the answer we will have is that y is less than x, or that y is not equal to x, and so on, meaning that we at least need 2 yes solutions where we will be on this side of on this region and say yes, they are not distinct because x is less than y, or yes, they're not distinct because, they are distinct because x is greater than y. We can expand this regions idea to a higher dimension. For example, in the third dimension, we will need 3 planes. One for x equals to y, another one for x equals to z, and one more for y equals to z. For x equals to y, we will have 2 possibilities. One is that x is less than y, or x is greater than y. Similarly, for the plane y equals to z, we have y less than z, or y greater than z. If we move the camera just a little bit, we can still see the 3 planes in the 3-dimension space. I went ahead and plotted some points. I know they're hard to see, but they'll come handy, because if we move the camera just right, we can still see a section of the planes, but we can actually appreciate that the 3 planes are separating the 3D space into 6 regions, from which I just label A through F. I know it's kind of hard to see the numbers, but believe me on this, that for region A, we have x less than y less than z. For B is x less than z, which is less than y, and so on, which kind of gives us an interesting pattern where it looks like I just have 3 letters and I'm just mixing them. It's just like a permutation problem now. Well, it is getting harder to visualize as we go higher and higher on the dimensions, but if we have an array of 4 elements, we can say that we'll be on the 4th dimension, and we just need to find all the permutations of 4 different axes, from which I just label A, B, C, D, and if you do all the permutations, you'll find out that you need 24 different regions. So if we generalize, we see that in dimension 1 we just have 1 yes solution. For 2 dimensions we need 2, for 3 we need 6, for 4 we need 24, and we can appreciate the pattern here. This is actually the factorial. So factorial, let's choose, for example, for 4 it will be 4 times 3 times 2 times 1, which is 24. So for the nth dimension, we can say we'll have n factorial yes solutions. Alright, math time. Here we go. If you can recall from previous slides, if we have the number of leaves in the decision tree, we can minimize the longest branch in the tree by rearranging it in an optimal way. If we do this, then the number of leaves will be approximately 2 to the h. If we solve for h, we'll have log of n factorial, since we knew we have n factorial leaves. And if we expand n factorial, we'll end up with n times n minus 1 times n minus 2 all the way to 1. So if we grab each element on this multiplication and we increase it to n, then we will say that n factorial is less than or equal to n to the n. So if we take the log of that, we'll say that log of n factorial is less than log of n to the n, which is n log n. But this is not enough to prove omega of n log n, so we can go another route as well. If we take these elements and we just grab half of it and we reduce them to n over 2, then we can say that n factorial should be bigger or equal to n over 2 to the n over 2. So if we take the log of that, we can do some math where we move the exponent to the side, then we move the 2 outside by subtracting. This is just going to be 1. So we end up with log of n factorial being greater or equal to n over 2 log n. So now we come with this statement where log of n factorial is greater than n over 2 log n, but is less than n log n. So we're in between what's n log n. So we can conclude that the number of comparisons in the worst case for the element distinctness problem is bounded by omega n log n. Thank you.